So, in science, whenever we are working with measurements, we can be working with very big numbers, we can be working with very small numbers. And those are going to be difficult to be represented. So, this is why we use a scientific notation to represent them. Let's say, for example, for this one is a very big number. So, to represent it as a scientific notation, first of all, check is it bigger than 1 or is it less than 1? So this number is greater than 1, right? So if it is greater than 1, this is what you need to do. Move the decimal point. So you do have the decimal place over here. Just go ahead and move it until after the first non-zero digit number. And count how many digit places did you move with that decimal point. So this decimal point, I moved it 23 places until it becomes after the 6. So the scientific notation over here is going to be 6.022 if you want to keep those numbers in there. And then the times, you move that decimal 23 decimal places. Normally, when your number is very big and you want to move the decimal point, the power is to the positive and not to the negative. So it's going to be 10 to the positive 23. So this is considered to be a scientific notation of this big number. If your number is very small, something like that, it's very small in there. We want to represent it. We cannot work with it like this. So we want to present it as a scientific notation. So if the number is very small, it's less than 1, then you pick up your decimal and you move it right after the first non-zero digit. So that's a 6. So here I need to be 6.25 in there. Because the number is small, the power is going to be to the negative. And here I'm moving it 21 places. So the number is going to be 6.25 times 10 to the minus 21. Same thing over here. This number is big, right? It's bigger than, it's greater than 1. So this one is greater than 1. Then I'm going to take that decimal point and I'm going to move it all the way to the right after the first non-zero digit. And the power is going to be to the positive. So here I will be moving it 6 places to be 3.56 times 10 to the 6. Let's have more examples in there. So write the following in terms of scientific notation. So always remember to check if your number is bigger than 1 or less than 1 so that you would know the sign of your power. So over here, this one is going to be your decimal. So we're going to move it as 1, 2, and 3 places in there. It's greater than 1, so it's going to be to the power positive 3 times 10 to the 3. This one is less than 1. Just move it right after the 6. It's going to be 6.45 times 10. I moved it 1, 2, 3, and 4 places, so that is going to be to the negative 4. This is 6, right? So it's going to be 6.0 in there. There is nothing to move. I mean, and I want to represent the 6 as sig fig. So to represent it as a scientific notation, it needs to be a number that starts with the first non-zero digit, and then you do have a decimal after that, and it needs to be to the power, 10 to the power. So for this one to be changed into a scientific notation, I need to use 10 to the power, but I don't have any power in there, so I'm going to make it 10 to the power 0. So the scientific notation for this one is going to be 6.0. 6.0 is 6. And 10 to the 0, we all know that any number to the any 10 to the power 0 is what? 1. It is 1. So it's as if 6.0 times 1. There are two terms to define whenever you are taking a measurement: accuracy and precision. And you want your measurement to be good accuracy and good precision. So accuracy is how close to the true value a given measurement is. So for example, here I do have 3 measurements. And one of the measurements is zero point 0.1, the other one is 0, and the third one is zero point 0.1 kilograms. You can see over here that it's poor accuracy because measurement number 2 is way off of the scale of the measurements between 1 and the 3. So it's poor accuracy, and at the same time, it's poor precision because all of these are different. All of these different measurements, they are completely different. So it's both poor accuracy and poor precision. So that is a simple bathroom scale. The lab balance, so if you go to the lab, the balance in the lab is more accurate than that of a bathroom scale, but still the precision is not going to be as precise. And the reason why, because see, the measurements here, they start the same, but after the decimal point, they are different. So we would say that this is a good accuracy because all of these three measurements, they are close to the true value, but how well the numbers are agree with each other or agreeing with each other, it's not much, so it is going to be poor precision. Now, going to the analytical balance, and this is what we normally use in the lab in order to mass the solids or mass liquids. In their analytical balance does have multiple significant figure digits after the decimal point, which makes it more precise and more accurate. So the measurements here, the three measurements, they start with 54, so this is a good accuracy. And as you can see, there are two digits, actually three digits after the decimal point in there that are the same. Only the last digit, which is not certain, this one is not accurate, so that will make the measurements to be precise. So by definition, significant figures, these are total number of digits recorded for a measurement or calculated quantity, and all the digits, all of them, you guys, all of them. So all the digits except the last one, except the last one is always estimated, the last one is always uncertain. Rules for counting significant figures. So when you start reading a number, of course, you read it from left to right, okay? So this is 423, 423 in there. The rule says that all non-zero numbers are significant. So I'm starting with 423. This is going to be three significant figures. This is all non-zero digits, so this is going to be five significant figures in there. Zero in the middle of the number is considered to be significant, so you have to count it. So number of significant figures for this one is all of them, and that is going to be five significant figures. This here is going to be five significant figures as well. This here, you count all of the zeros, you guys. This is seven significant figures. Zero at the beginning of the number are not significant, so these zeros in there are not significant. All the zeros, whenever you're starting with a number, all the zeros before the number are not significant, so you do not count them in your measurements. So all of these are not significant, so the total number of significant figure is here three significant figure. So if I want to change this into a scientific notation, change the color. If I want to change this into a scientific notation, let's move the decimal point into the first non-zero digit. It's going to be 6.61 times 10 to the, since my number is less than 1, then the exponent is going to be negative, and I moved it three digits in there. 0.15, this one is going to be two significant figures. And if I want to represent it as a scientific notation, I just moved it once. So that's going to be 10 to the negative 1 because the 0.15 is less than 1. This one again, all of these are sig figs. The ones before the 6, they are not sig figs. The zeros before the 6, not significant figures. So this is going to be 4 significant figures in there. And if I want to represent it as a scientific notation, it's going to be 6.005 times 10 to the negative 2. Now, zeros at the end of the number. So zeros at the beginning of the number, zeros at the beginning of the number, they are not significant. However, zeros at the end of the number, they have to be significant because this is part of your measurement. So anything after the decimal point, so it needs to be after the decimal point. So anything after the decimal point doesn't matter. Number, zero, it really doesn't matter. These are significant. So this over here is going to be 5 significant figures. This one, these are part of your measurements. So a 92.0000 is precise. It's more precise than just 92. So these are all significant. So this is 7 sig figs. All of those are significant figures. So that is going to be 8 significant figures. 0 at the end of the number. Now, you don't have a decimal, right? So if you don't have a decimal, zeros are not considered to be significant. So over here, all of these zeros are not significant. So this is going to go all the way to be 1 sig fig. So I only count the 6. Here I only count the non-zero digits, which is basically 4 significant figures. Here, this one is going to be 2 significant figures, and this one is going to be 1 significant figure. So to sum up, when you are working with zeros at the beginning of the number, they are not significant. Zeros at the end of the number, they are not significant unless they are after the decimal point. So if they are after the decimal point, then you have to consider them as significant figures. Rounding, whenever you are rounding, there are rules for rounding. So if the first digit you remove is less than 5, please round down by dropping it and all the following digits. So something like this over here, I just want to go ahead and remove the 4, right? So I'm just going to look at 4 and see 4 is less than 5. So because it is less than 5, I'm just going to drop it, and my number is going to be 5.6065. If the first digit you remove is 5 or greater, okay, round up by adding 1 to the digit on the left. So let's say, for example, if I want to go ahead and remove this guy over here, the 5. So I look at the 5 and I know that 5 is 5 or greater, right? So I'm just going to go ahead and remove it, but I'm going to add 1 to the 6. So my answer is going to be 5.7. And this is a rounding to 2 significant figures. This is a rounding to 3 significant figures. If the first digit you remove is 5 and there are more non-zero digits following, just round it out. So for example, over here, I am just removing the 5 in there. Since I am removing the 5, 5 is 5 or more, so I have to add 1 to the 4. So that is going to be 5.665. Just round that. For the math rules, multiplication and division and significant figures, okay, you need to keep in mind that your answer cannot be more significant than either of the original numbers that you are working with. The rules that we're going to follow for multiplication and division and sig figs is different than those for addition and subtraction. So for multiplication and division, you're going to look at both numbers that you are working with and see which one has less significant figures. So the one that has less significant figures is gonna be simply your answer is gonna follow it, because your answer cannot be more accurate than or more precise than the least significant figure number. So here I do have 3 significant figures and 4 significant figures. So my answer in this case has to be 3 significant figures. When you divide, the calculator is going to give you the answer. So whenever you get the answer, just make sure to round up so that you have 3 significant figures and not more than that. Let's have an example over here. So provide the answer of the following using the significant scientific notation. So I need to change that into a scientific notation after I get my my answer. I kind of like solve this one as a start. So you start by calculating the number of significant figures for each of those numbers. This is a 2 sig fig. This is a 4 significant figure in there. Put it in the calculator, get the answer. And once you get the answer in there, you want to make sure that your answer follows the least precise number, which is the 2 significant figures. So my answer has to be 2 significant figures in there. So if it needs to have 2 significant figures, I need to drop all of those. 8 is more than 5, so I need to round the 3, and my answer in this case is going to be a 4, and a 0. Don't forget the 0. It's not 44, it is 440 in there. I need to write it as a scientific notation. So this one is greater than 1, right? So I need to move it 2 decimal places. It's going to be 4.4 times 10 to the 2, and that is a 2 significant figure. And this one over here is a 2 significant figure. Please remember that 0 is not a significant figure if it is as a whole number. So this 0 over here is not considered to be a sig fig. Let's have another example here. So 4.36, this is a 3 sig fig. This one is a 2 significant figure. So my answer has to follow 2 significant figure. That is the answer that is given in the calculator in there. So I need to make it 2 significant figures, and I know that all of those are not significant. So that is going to be 0.00. I need to drop the 6, so it's going to be 5. I missed the 0. So this is a 0 over here. And then it is a 5, 7. If I want to go ahead and write it as a scientific notation, so it's 1, 2, 3, and 4. So the answer is going to be 5.7 times 10 to the negative 4. That is its scientific notation. Okay, so for this one as well, 4 sig fig, 3 significant figures. So your answer has to be a 3 significant figure. Just put it and get your answer in the calculator, and then go ahead and round up and make sure that you get your answer in a 3 significant figure, because this one is the least precise one. So 3 significant figures, this means that I need those 3 numbers in there. The 0 is less than 5, so I'm just going to drop all of these numbers. So it's going to be 6.88 times 10 to the negative 42, and this is a scientific notation as well. This one has to follow 3 significant figures, so I need to take the first 3 measurements in there. 6 is more than 5, so I have to add 1 to this one there. So it's going to be 5.02 times 10 to the negative 2, and this one is going to be 3 significant figure as well. Now for the addition and the subtraction. The answer cannot have more digits to the right of the decimal point than either of the original numbers. And this is how we do it, okay? So we put the numbers in there. Here we're performing a regular addition. So we put the numbers underneath each other, and then we go ahead and look at the least precise number. The least precise number has 2 digits after the decimal. So now here, you don't count all the sig figs like you did in the multiplication and the division. You just look at the decimal and see how many digits after the decimal. And that is going to be similar to your answer in there. So the least precise number has 2 digits after the decimal, then your answer should have 2 digits after the decimal. Please make sure that you round as well. So let's have an example. Here are 3 numbers in there that I am adding those up. One of these numbers have no digit on the after the decimal. So this one has 2, this one has 1, and this one has none after the decimal. So my answer should have none after the decimal. So when I am adding this up, that is going to be 37. So it's 0.37, but I don't need that 37 in there because my least precise number has no digits after the decimal. So my answer here is going to be 306. These are more examples in there. So my least precise number has 1 digit after the decimal. So my answer has to round up to be 1 digit after the decimal. So the right answer here is 84.7. This one has 3 digits after the decimal, so my answer needs to have 3 digits after the decimal. So these are the 3 digits. 3 there is less than 5, so I'm just going to drop all the numbers, and this is going to round to 0.0324. Okay, now let's say if I have a multiple step in there. I have a subtraction versus division. Normally what you do is you can plug them in the calculator and then figure out the significant figure, or you can go ahead and do them separate. So you do the subtraction alone, and then you do the division alone in there. With respect to, and your answer is going to follow the division. Okay, so over here what we have is 3 digits after the decimal, so we're going to keep 3 digits after the decimal. Here it's two sig figs. So I have two significant figures, four significant figures, so my answer is going to follow the two significant figures. There is an additional sheet on eCampus for more practice on significant figures, and it does have its solutions as well. So please go ahead and practice that. It is not a homework, it's just a project.